ATSC 3.0, known as well as Next Gen TV, is the latest major standard to have been implemented and deployed in the broadcast sector. In this tutorial video, we will review all the tools available in the ATSC analyzer for tests of the different layers of an ATSC 3.0 signal. First of all, we will head to the TV analyzer mode in order to look for our ATSC 3.0 signal carrier. Once we tune its central frequency, the meter will initiate a search to discover its signal standard and modulation characteristics. Once the signal is identified, we can see the screen bottom bar to light up in green. Indeed, we are informed that this carrier is an ATSC 3.0 signal. If we press at its side, we can see how many PLPs, physical layer pipes, form this signal. In this case, we have two of them, numbered 0 and 1. We can set up one of the smaller panels to show us the signal modulation parameters for the PLP selected. As you can see, these are different for these two PLPs. PLP1 is a 64 QAM modulated signal, while PLP0 is a 256 QAM modulated signal. We can confirm this by getting into the Constellation tool. Besides, each PLP will be carrying a set of different services. We can check this selecting the video tool and pressing on its screen. A window will open up where we can find the names of the services carried by the chosen PLP. ATSC 3.0 specifies the use of the following standards for the encoding of video, audio, subtitles, caption information and signaling data. For video, HEVC encoding is used, with a color subsampling of 420 and maximum spatial resolution of 2160 by 3840 pixels. And for audio, AC4 encoding is used. Service delivery over broadband makes use of root dash and MMTP protocols. These packets are then encapsulated into UDP-IP and TCP-IP packets for their transport. The video, audio, and data content for each service can be inspected by selecting the desired service and selecting video-audio parameters. You can as well inspect the manifest, a file that will be retrieved by the receiver which contains a description of all the contents included in the root dash and MMTP segments being received. All the different packets from the network layer, that is, packets carrying video and audio services, and packets carrying signaling data, captions and subtitles, they all converge in the link layer, where they are all encapsulated together in one single common packet format called ALP, for its delivery down to the physical layer, in the transmitting end and back to the network layer at the receiving end. The recording tool will allow us to record the ALP signal with the ATSC analyzer. The preamble is a part of the ATSC 3.0 signal that carries data that allows ATSC 3.0 receivers to tune themselves to the modulation parameters used for transmission, that is, input formatting, code modulation, framing structure, etc. The signaling data is transmitted partly in the preamble, as well as in the form of bootstrap signals. The latter is a robust signal that allows the receiver to estimate the RF channel, discover and decode the received signal, put together a service list, and convey emergency alert system alerts. But its most imperative function is to allow for the receiver to log to the received ATSC 3.0 signal. We can find extensive information about the bootstrap and preamble as well as the metadata related to each PLP and subframe in the Signal Parameters tool by inspecting the corresponding tab. Once there, you will need to maximize its panel to see the information in full. At the physical layer, the 6 MHz ATSC 3.0 carrier is split into thousands of non-interfering subcarriers by using COFDM. A guard interval is used after transmission of each set of symbols in order to make the signal resilient against echoes and transmissions from distant transmitters under SFN network operation. We find a whole set of tools aimed at analysis of the ATSC 3.0 signal physical layer. The first of them are the measurements of power level, carrier to noise, MER, link margin, CBR and LBR of the carrier tuned, which we can find in the tool Measurements. Secondly, we can find more information of the signal parameters related to the physical layer in the Signal Parameters tool, such as the FFT size or number of carriers, guard interval size, scatter pilot pattern, and so on. Given that ATSC 3.0 carriers are COFDM modulated in the physical layer, we can use the MER by carrier tool to check the MER value of all the COFDM carriers. Here, in the horizontal axis, we can see the number of carriers, while in the vertical axis the MER value is shown. On the bottom area of the panel, we can see the average MER value among all the carriers, and the standard deviation for the MER. Wherever there is an interference signal, a drop in the MER of the affected carriers will occur. If you press on any of the carriers, you will see the MER measurement for that carrier in the MER field at the bottom area, along with the carrier number. The echoes analyzer can detect and display the echoes that can occur due to the multiple reception of the same digital terrestrial ATSC 3.0 channel with different delays. It is a formidable tool in order to visualize these echoes and assess the potential damage they may cause to our signal. This graph is showing time in microseconds in the horizontal axis and level in dB carrier units in the vertical axis. As many as 10 echoes can be displayed simultaneously in the graph. Everything falling in between the red areas are echoes being received within the guard interval, whereas everything falling in the red areas is outside the guard interval and therefore very damaging. For each echo we can read its related level when compared to the main signal, its delay in microseconds when compared to the main signal, and its distance in kilometers to the source compared to the main signal's distance to the source. You can find more details about this tool in our specific tutorial video about the echoes analyzer. We recommend that you take a look at the article we released some months ago about ATSC 3.0 in case you have any doubts about the technical details on this standard. More tools will come up in the near future, such as the shoulder attenuation measurement, so stay tuned!